So in this example, we want to find f explicitly using the condition f0 equals 5, f prime of 0 equals 16. So, well, basically, we have a diagram. If you take derivative of f, we will get f prime. Then take derivative further to get f double prime. So now that f double prime is given, you want to go backward and take antiderivative of f double prime to get f prime. And then eventually, we take antiderivative to get original function f. So first we take an antiderivative of f double prime. So take the most general. So we take the most general antiderivative. General antiderivative. Then f prime, derivative of f double prime. So f prime is going to be, the first term will give you negative 2x, and then x squared 1 over 2, and then 18 will survive like that. Then x cubed 1 over 3 times 12 plus constant c. Let me call it c1 to distinguish that from the next or second constant. So f prime is more or less this cubic function up to coefficient. And now that we have condition f0 equals 5, we can determine c1. So f prime of 0 is 16. So when you plug 0 into f prime, we have 0 plus c1, which should be 16. And we know c1 is 16. Okay, for f, we take antiderivative again. So negative 2x will give you negative x squared. And then this is just 9. So for this new power, we need 1/3. And this is just negative 4. And again, for this new power, we need 1/4. And then our constant is 16. So this 16 will give you 16x, and then constant. And we have a condition saying f0 is 5. When you plug 0 into this function, we have 0, 0, 0, 0, and then c2. That should be our f of 0, which is 5. Good. So it turns out that our f is a quartic function with the constant 5. That's it. This is the explicit expression for function f. Okay, in this example, we want to discuss some application of antiderivative in physics. So a car is traveling with some speed, and then probably the driver found some obstacle or decided to stop. And the driver applied brake. And the brake performance is given by this number, deceleration of 10 feet per second squared. And you want to know when this car stopped, or how much this guy traveled before stopping. So we need to read this problem carefully to find which functions are given or which antiderivatives we need to take. So in this deceleration, well, this deceleration gives you acceleration. So we can use this information to get a function, say a of t, which is just constant, 10. So we need to be careful a little bit. This is a deceleration. Now that acceleration has some direction or sign, you need to be careful to determine this sign. Now that the speed is decreasing, this acceleration is negative. Or deceleration means negative acceleration. So you want to use negative 10. So we have a constant function for the acceleration. And then you take antiderivative to get velocity, v of t, negative 10t plus, of course, constant, c1. So we don't know what it is, but we will figure this out. So velocity is given by this linear function. And then to determine this c1, we need to fix some time frame. So the problem doesn't specify any time frame, but you need to determine or fix some time frame. So it's reasonable to say the driver started to apply brake at time t equals 0. So at that moment, speed is given 20 feet per second. So we can use this condition to determine c1. So when t equals 0, velocity is 20. So v of 0 is 20. So c1 is 20. Good. So we have negative 10t plus 20. Very good. And then we take antiderivative again to get position function. So say s of t. Antiderivative of this, 20t plus another constant, c2. Okay, again, to determine c2, we use this time frame. For this position function, you may declare that this is the origin. So at t equals 0, the position of car is at the origin. So you can declare this is a positive direction, and you want to know how much the car travels until it stops. So this is s equals 0 position or the origin. So we can say s of 0 is 0. So we have full information for s of t. This which is just quadratic function, negative 5t squared plus 20t. Good. Once we figure out the time, we plug that into this position function to get the displacement or the distance, s of something. So we want to find this time. Again, this problem doesn't specify the time, but now that we have full information for the velocity, we can find this time. We are interested in the time when the car stops or when the velocity is 0. So the car stops when velocity becomes 0. So we solve linear equation, negative 10t plus 20 equals 0. So t is simply what? 20 over 10? 2. Good. We got the time when the car stops. So the car stops after 2 seconds, and we are done. S of 2 is negative 5 2 squared plus 22. So then 40 minus 20. 20. So it turns out that the car travels 20 feet further before it stops, and it takes 2 seconds. So I try to pick simple numbers, but this problem is important in a sense that you need to declare the time frame, and you need to determine constant C1 and C2, although the problem doesn't specify further information. So you need to be creative to determine C1 and C2 and use appropriate time frame.